Now let's talk about the last topic, which is test benches. And we're going to use test benches. These are not synthesizable. This never turns into hardware. But test benches are for helping automate our simulations. So we don't have to laboriously go through and set the inputs and maybe toggle the clock. Instead, we can use a test bench and perhaps we fix something in our module and then we can rerun the test bench and see how it worked. So a test bench is an HDL module that tests another module, and this module that it's testing is called the device under test, or the DUT. You'll also see it called the unit under test, or the UUT. So this is not synthesizable. A test bench is not synthesizable. This is just for simulation only. And let's talk about 3 different types of test benches: a simple test bench, self-checking, and self-checking with test vectors. So they're going to kind of build upon each other. So let's start by writing the system Verilog code for the module under test, the device under test. So this is some simple function y equals b bar c bar, or a and b bar. So pause the video and write a module for that function. Okay, so we write this module. We have the keyword module, the name of the module, the inputs a, b, and c, the output y, and now we specify the function, assign y equals b bar c bar, or a and b bar. So this is our device under test, or the module that we're going to test in our test bench. So here's the first version of the test bench, the simple test bench. So we have the keyword module, and then our module name, in this case Testbench1. You notice there are no inputs and outputs. We have some internal signals A, B, C, and Y. And now we're going to instantiate the device under test, the silly function module. DUT is the instance name. And we connect it to A, B, C, and Y. And now we probe these input values, A, B, and C. So we set A, B, and C all to 0 to start with, and then delay 10 ticks in simulation. Again, remember this is just simulation, and test benches generally are just for simulation. They cannot be synthesized. A, B, and C are 0. We pause for 10 or delay for 10 ticks so that we can see the output on the simulation waveform. Then we make C1, so now we have 0, 0, 1. Again, delay so we can see the output Y, how the output Y changes. 0, 0, 1, 0, 0, 0, 1, 1, and so forth till we have all of the input combinations. This final one is going to be 1, 1, 1 on A, B, and C. And now we run this and we can look at the waveform, but instead of having to do this manually, setting our A, B, and C values and then delaying the clock, we can just run this simple test bench. And so we can, but then we have to still manually view the waveform to see if we got the correct result on Y. This is the second test bench. We're going to use a self-checking test bench. And so this part looks the same. Renamed it Testbench2, but everything up here is the same. And now we start, this initial block occurs at the beginning of the simulation. And so now, in addition to setting the input values, A, B, and C are 0, and then waiting 10, we also check the output. We say, oh, for this one, because of our function, Y should be 1. So if it's not equal to 1, display this on the simulation monitor, on the the text output of the simulation. So display, hey, the 0, 0, 0 input combination failed, and we make C1, so now 0, 0, 1. Y should be 0 in this case, so if it isn't, then print that this failed. Of course, you could make an error in this, right? You could think it should be 0, but it really should be 1. So now they're, it's a little bit more complex and also more opportunities for making errors, but saves a lot of time, right? So instead of having to go through the waveform and seeing, okay, for 0, 0, 0, there's A, B, and C, 0, 0, 0, 0, 0, 1, 0, 1, 0, and then we have to look at what the output of the actual module did, and we see, hopefully we see it correspond to what we expect, blah, 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 whatever it did. Instead of having to go through and look at why, now we can have the test bench test for it. Hey, we expect Y to be 1 here. If it isn't, display some text that failed. Expect it to be 0 in the 0, 0, 1 case, ABC equals 0, 0, 1. Otherwise, just print that it failed. And then after we see the failure messages on our simulation, we can go back and check the waveform for those as well. So this is a little bit more automated, but it's kind of annoying still to write ABC 0, 0, 0, 0, 0, 1. Kind of be nicer to output as a truth table, right? For the 0, 0, 0 combination, we expect to get 1. So here's our A, B, C, and expected Y value. Y expected 0, 0, 1. We expect to get 0. 0, 0, 0. Expect to get 1, 0, 0, 1. We expect to get 0. 0, 1, 0, which is this case, we expect to get 0, and dot, 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 until finally the last case, 1, 1, 1, we expect to get 0 as well. And so it'd be a lot nicer, this is basically our truth table, to input that as text instead of having to input it this way and just read that text file. Then it's super easy to change too if we made a mistake. Oh, I actually, in this case, it's not a mistake, but for that combination, it should be 0 instead of 1. I just change the text file that I read, or essentially the truth table. Dot, dot, dot. So we're going to now upgrade this test bench 2, into a third test bench, and this is the final type of test bench, and this is the one that we use most often. This is a test bench with test vectors, and these test vectors are basically those truth table rows. So the test vectors is this 0, 0, 0, 1, showing A, B, C, and the expected Y value. This is called a vector. So these are our test vectors for the 0, 0, 1 combination. We expected 0, or 0, 1, 0, expected whatever. So for this test bench, we're going to generate a clock for assigning inputs and reading outputs. We'll read these test vectors file into an array. We'll assign inputs and the expected outputs, and then compare for a given input the outputs with the expected outputs, and report errors just like we did in the last one, the last test bench, where we report if the actual output from the module, from the device under test, and the expected outputs didn't match. So we generate this clock, and on the rising edge of the clock, so now we're using the clock basically to delay the time we assign the inputs and then look at the outputs. So it's basically doing that, the #10, right? This is saying, hey, delay for a bit, let the module calculate what the output should be, and on the falling edge of the clock, and the clock goes from 1 to 0, that falling edge, we're going to compare the outputs. And then the next edge, assign new inputs, compare the outputs, new inputs, and so forth. So this clock is basically helping us just produce that delay, where we want to assign inputs and then wait for a bit before we compare the actual outputs of the module with what we expect. If our device under test is a synchronous circuit or synchronous sequential circuit, we can also use the clock to run that circuit as well. So here's an example test vector file. This is basically what we just drew on the prior slide. example.txt. This is just a text file. Comments are ignored, but help us remember what these are. So here's ABC. So when they're all zeros, we expect output Y to be 1. When it's 0, 0, 1, we expect it to be 0, etc. This is not the actual output Y, because the actual output Y, we're setting the inputs A, B, and C, but then the module, the device under test, is giving us Y. These expected values we're going to assign to some wire, some signal, Y expected, and then we're going to compare, hey, is what I expected the same as what I actually got, or Y and Y expected the same. So here we have the test bench 3. We have, it's, it seems a lot more complicated. We have our clock reset, A, B, C, and Y expected. The reset is there so that if it is synchronous sequential, you can reset your synchronous sequential logic at the beginning of the simulation. And we have our inputs A, B, C, our output Y. Then we have that extra wire Y expected. And now we have these kind of bookkeeping variables, vector num and errors, and also an array of test vectors. So this 3:0 is saying the width of this array. So we have a 4-bit width, and this happens to be have 10,001 entries, so 0 up to 10,000. And we won't use all of those, but just made it larger just in case. And so we're going to instantiate our device under test, just like we did before. And now we have this always block that generates the clock. Because there's no sensitivity list, it always executes. So we have always, no sensitivity list. Begin, clock equals 1, 5 ticks later, clock equals 0, 5 ticks later, and it will repeat. So it's going to go 1, 5 ticks later go to 0, 5 ticks later go to 1, ... That's our clock generation. And at the start, again, this initial block runs at the beginning of the simulation. And we're going to start by reading memory. So read mem B. B says it's in binary format. And we're going to read this. This should be example.txt, that file of test vectors, into our test vectors array. So we happen to call this example.txt. And we're going to read that into our test vectors array. And remember that test vectors array looks like this. And so it will read 0, 0, 0, 1 into entry 0 or index 0, 0, 0, 1. And those underscores really aren't there, right? Those are just for us. So that's why it's a 4-bit wide array, 0, 0, 1, 0, 0, 1, 0, dot, all, etc., right? In our case, we'll have entries from 0 to entry 7, but we just won't use the rest of the entries in the test vectors array. Okay, so this line reads the test vector file into the test vectors array and resets the bookkeeping variables, vector num and errors. So there are no errors, and we're going to start at vector 0. So vector num is 0. And we're going to toggle reset. So assert reset for 22 clock ticks, and then simulation ticks, and then make reset back to 0. In our case, our device under test doesn't have a reset input. It's not synchronous sequential logic, so that doesn't really matter. But for synchronous sequential logic, you'll want to reset the system to start. So a note here is that we could have read, or we could have written our test vector file in hexadecimal, and then we would have needed to use the read mem h call instead of read mem b. So if we had written, for example, so we had 0, 0, 0, 1, 0, 0, 1, 0, we could have written that in hex and said 1, 2, ... whatever the next lines are. But then we would have had to have read it in using read mem h. Okay, so we're going to apply the test vectors on the rising edge of the clock. So always at pause edge clock, we're going to delay just one tick and say, okay, I'm going to assign ABC and the expected value of y. So ABC is assigning the inputs to the device under test, but it is not assigning the output y. That will be driven by the device under test itself. But it is assigning this extra wire over here that's called y expected. And then on the falling edge of the clock, always at neg edge clock, we're going to skip this test if reset is 1. So if not reset, that means reset is 0. Check if y is equal to y expected. So the output from the device under test being driven by A, B, and C, is it the same as that wire we assigned, that y expected wire we assigned from the test vectors? If it's not equal to that, so we have this not equals equals, it's not equal, y is not what we expected, then we display, hey, we had an error, and this was the input combination that we had, A, B, and C, and this is the output we got, and this is the output we expected. So this is in the order of the arguments. So we have a %b that says print it in binary. It's that first argument after the quotes, and this next argument after, before the quotes corresponds to the y expected. And we increment this bookkeeping value errors. So errors equals errors plus 1. And we could have printed, for example, things in using hexadecimal. For example, A, B, and C, we could print in hexadecimal. In this case, binary makes sense, but you could also, sometimes hexadecimal makes more sense. And we're going to increment the vector num. So in our test vectors array, we have, we read the first one, and then the second one, right? So it was 0, now it's going to increment to 1, and it will use that to assign at the next rising edge of the clock, ABC and y expected. And so now it checks and says, hey, are we done with valid values in the test vectors array? If it's test vector subvector num, so for example, after the first run through, we had 0 plus 1. If test vector sub 1 is undefined, 4 bits of binary x, then we're done with, there are no more test vectors to assign to the inputs. And so in this case, that wouldn't happen until vector num equals 8, because test vector 0 through 7 are defined. But once vector num is 8, it would get to, okay, vector num is 8. Okay, these are undefined. They're equal to 4 bits of binary x. And then we would print this kind of summary statement of completed. In this case, it would say 8 tests completed with however many errors happened. So remember, this first %d corresponds to this first argument after the quotes, and the second %d, the second argument. We could have, more. If you had more %d and wanted to print other things, we'll just have more arguments listed here. Okay, and then if we don't have any more test vectors, then we stop at the simulation, and you can view the results in the waveform viewer of the simulator. So why do we have equals, 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 and not equals, equals? So it seems like there's an extra equal sign. The reason we use that is because those can compare on not just 1 and 0, but also x and z. So undefined and floating. So if you're changing this this test vector, this test bench, and you're using it to test another module, let's say it has 5 inputs and 1 output, they're all 1-bit inputs, then you would make sure to change this. So with 5 inputs and 1 output, all 1-bit bit width, then you would change that to 6-bit binary X. So that's a common error. People forget to change that bit width there.